We've already looked at how various types of hydropower plant work, and this type is not much different from some of the others we've seen. However, it's got quite a unique operating characteristic, which I'm going to discuss with you in a moment. So we can see we've got our water inlet, and that is on the opposite side of this reservoir wall. I'll spin around so we can actually go down and have a look at the inlet. There is the inlet. We can see we've also got a gate, so we can close off the water inlet to the penstock. We've then got our penstock, which comes down, comes all the way down the hill. This is actually quite a large head of pressure, or a large head, to have with this type of power plant. Now, having a large to medium head is a characteristic of a pump storage power plant. What's unusual here is that the penstock is split into two and feeds two separate turbines. Remember, you don't normally see that on power plants where you have a medium to large head. Normally, one penstock will supply one turbine. Now I'm going to go and have a look at the turbines and generators from the outside, because I did actually try and look earlier from inside and it's quite cramped. We can see that we've got our turbine runner, which is housed within this casing, and the water itself comes from the penstock. You can see it coming in here. It's fed to the turbine runner, and then it's discharged, and it will go out through the draft tube and into the river. We'll see if we can find the draft tube, and this is it here, and on the opposite side we also have another draft tube. So this is very similar in a way to some of the other hydro plants that we looked at. It's just that the head is much larger. If we've got a larger head, then that means we can have either a Pelton type turbine or a Francis type turbine. We're not going to have a Kaplan type turbine because the head is simply too large. Pump storage power plants, though, only utilize a Francis type turbine. They do not use Pelton type turbines or Kaplan. And there's a very simple reason for this. Francis type turbines can be used to pump water back up the mountain. That means we can generate electricity when water flows down the mountain, and then we can pump the water back up again to the upper reservoir in order to refill the upper reservoir. But why would we do this? Why would we pump water back up and then let water back down again later? Well, a pump storage hydropower plant is very similar to a battery. Except we're not storing chemical energy, we're actually storing the potential energy of the water at a higher elevation. Let's imagine for a moment that it's a very sunny, windy day. And that means that we're generating a lot of electricity from wind turbines and solar power. This also means that electricity is cheap, it's in abundance. So imagine we're paying 1 cent per kilowatt hour, just to keep things simple. Now it might be that the people operating this pump storage plant think that 1 cent per kilowatt hour is very cheap, and they'll buy the electricity in order that they can power the Francis turbines and pump the water from the lower reservoir, in this case a river, up to the upper reservoir. And they'll do this all day because it's been sunny all day and there's also been a lot of wind, so we've got a lot of cheap electricity. When the upper reservoir is full, and this may take 8 to 10 hours, maybe more, maybe less, we'll hold on to all of this stored potential energy. And what we'll do, we'll wait until it's dark, and all of a sudden, all of that abundant electrical supply that was provided by the sun from solar power, and maybe the wind dies down as well, all of that abundant electrical power will disappear. It will no longer be available in the national grid. Now, because we have a free market, whenever we have something in abundance, it's not very valuable. Whenever something becomes scarce, its value increases. Now, this is the same with electricity. So there's no longer an abundance of electricity in the national grid, and it may be that the grid operator is willing to pay 2 or 3 cents per kilowatt hour that we sell to the grid. So if we open the valves and the gates and everything else and we allow the water to flow down to our turbine runner, we can then begin to generate electricity. And because we've pumped so much water into the upper reservoir, we may be able to do this for several hours or longer. As the water flows down and we generate electricity, we're making money. We're making the difference between what it costs to pump the water up the mountain, which was 1 cent per kilowatt hour, and the price that we're getting now, which may be 2 or 3 cents per kilowatt hour. In the past, the actual operation of a pump storage plant would be very regular. Because coal-fired power stations and other thermal plants often stay online day and night and do not cycle on and off because they're not capable of that, especially not on a daily basis, there was an abundance of power available at night. And these pump storage plants would come online at night time and they would use some of this abundant electrical power to pump water up to the upper reservoir. And that was how things stayed for about 30 years. In the morning, when people started waking up and the electrical demand was very high, we would use pump storage plants to deal with these peaks in electrical power consumption. Remember, pump storage plants can come online very, very quickly, typically in less than a minute. So any large peaks that we have in our grid, we can cover those using pump storage power plants. Now this setup continued for about 30 years. And then we started getting renewable energy sources coming more and more onto the market. And I'm talking here mostly about wind turbines and solar power generation, typically PVs or photovoltaics. When renewables came online, the whole industry changed. The reason the industry changed is because suddenly there was an influx of power available during the day. If we had a very sunny day, then there would be a lot of power generated by all of these solar panels. If it was very windy, there'd be a lot of power generated by all of these wind turbines. And all of a sudden, instead of having to wait until night when the power demand dropped and pump storage plants could actually purchase the electricity at a better price, they were able to purchase electricity at a cheaper price during the daytime and at night. So the dynamic in the power industry slightly changed. So at the moment, it's a very good time to own a pump storage power plant. There's a lot more opportunity to make a profit than there used to be in the past. I'm actually a big fan of this type of power plant. They give the grid operator good flexibility concerning frequency regulation and voltage regulation of the grid, and they have a high level of dispatchability. Remember, we can have the entire plant online in less than a minute, and that is very, very fast compared to a coal-fired power station, which may take a day or 2 days to come fully online. So a very unique and interesting type of hydropower plant. Perhaps one of the most interesting aspects of this type of power plant is that we can store the energy. Remember, we can have an upper reservoir like the one we're looking at now, and we can store all of that potential energy and turn it into electrical energy on demand. That is a very unique feature for this type of plant, and it's a very unique feature in the power plant industry generally. The only problem with this type of plant is that you need very unique geological features in order to have this type of plant. We need a difference in elevation that is quite large, and you can see that here because the penstock is running all the way up the side of the mountain. Sometimes you'll actually see these types of plants where the powerhouse will actually be built into the mountain. That's not unusual. And the penstocks themselves will also be built into the mountain. So there'll be very little of the power plant that you can actually see other than the upper reservoir at the top and the open air switchyard, which will be down at the bottom. Because you need an abundance of water and you also need these geological features that allow you to bring a body of water from the upper reservoir to the lower reservoir, with quite a large head between the upper and lower reservoir, you're very restricted on where you can actually have these types of plant. Somewhere like Norway is ideal because there they have very rocky and rugged terrain with a lot of water. A place like Switzerland is also ideal. They have hard rock, they have deep valleys, they have a lot of opportunity to capture water at a higher elevation and then to allow it to run down to a river and pump it up and down on demand. Somewhere like the middle of Germany is less ideal. The change in elevation per square mile is rather low. You're more likely to get hills or plains than you are likely to get these large mountains with sudden drops in elevation. Most of Europe has already exploited its pump storage capacity, And it's becoming more and more difficult to build this type of plant for the same reasons as with other types of plants. There are environmental factors to consider. If you want to build a pumped storage hydroelectric plant in Central Europe, you're going to find it quite difficult because often these plants will be located in remote areas. Sometimes they may even be located in areas that are protected. Building an upper reservoir like the one we're seeing now is very, very difficult to get planning permission for. There are a lot of environmental agencies that will be against building this type of installation within a wildlife area, especially if the area is protected. Not only that, there are other factors that you need to consider. If we go down to the bottom of this 3D model and spin around, you can see here we've got things like electrical transformers and open air switch yards and generators and turbines. These items of machinery require maintenance, which means you need to build a road out to the plant. Again, this may be difficult to get permission for. All of the machinery associated with this plant may also need to be environmentally friendly. What I mean here is that the electrical transformer is often full of oil. This is an insulator, and it's a requirement for very large transformers. Now, it's possible to get biodegradable oils and fill the transformer up with these, but they are incredibly expensive. This is another factor that you have to factor in when you're wanting to build one of these power stations. Is the power station going to be within an environmentally protected area? And if it is, what does that mean for all of the equipment and machinery that is going to be operating in this area? If, for example, we were using oils and greases to seal the turbine runner space between the runner and the generator, what happens if some of this oil and grease leaks into the water here and then starts going downstream? Again, you need to have biodegradable, environmentally friendly oil and greases. These also cost more money. So there are little things that need to be taken into account with every type of hydropower plant. There are always good, large advantages, and there are always some disadvantages. But as I say, a very unique type of plant, one of the very few that allows us to store and release energy on demand, but also one that requires very unique geological features in order that it can be put into service.